Hello, everyone. I hope you can hear me well. I hope you can see me well. My name is Ilya Jackson, a postdoctoral associate at MIT Center for Transportation and Logistics. And today I am privileged to present you the study, AutoML Approach to Classification of Candidate Solutions for Simulation Models of Logistic Systems. The outline of the presentation fully reflects the structure of the paper. So, real-world dynamic systems frequently require operational decisions on repetitive basis, and the many faults of such systems can be found in the context of supply chain management, logistics, and production. Decision makers work under constant pressure to make critical decisions quickly. That's why the decision support system must produce yes or no conclusions with confidence and nearly perfect accuracy. Therefore, prediction in general and binary classification in particular are core elements of decision making. However, several obstacles arise. First, predictive models, especially state-of-the-art, require the sheer amount of data, huge amount of data. And the physical systems cannot frequently provide the necessary amounts, even if the systems are stuffed with sensors and IoT devices. Second, the complexity, dimensionality, and stochasticity of many real-world systems frequently make analytical approaches inapplicable or hard to apply. Simulations can be used to overcome both obstacles. For example, discrete event simulation models allow one to model complex stochastic systems in the most straightforward form, namely in the form of executable computer program. The problem is that if simulation models are too complex and detailed, the computational burden, the computational budget can be substantial. In this case, it's reasonable to take advantage of an alternative, cheaper to compute model, also known as meta model. Roughly speaking, a meta model is the model of the model built specifically to approximate the output of interest of the original simulation model with a sufficient degree of accuracy. However, insofar as yes-no decision regarding a candidate solution is a primary consideration for many problems in logistics and supply chain management, it appears to be reasonable not to approximate an exact numeric outcome, but rather to classify it in accordance to a particular criteria. For example, profitability, whether it leads to positive net profit or not. Metamodeling can be easily reframed as a classification problem if we consider a simulation model as a nonlinear input-output map, sort of a black box function. Output is a stochastic variable, and the average value can be estimated based on n runs or n replications. If we repeat this procedure in the loop, if we conduct experiments with the simulation model, a dataset tau can be obtained. After that, we may label data based on a specified criteria, for example, profitability, whether the output y, net profit, exceeds 0 or not. After that, we may train any machine learning algorithm by minimizing the cross-entropy cost function in the attempt to maximize F1 score or any other accuracy-related metric. For such tasks, artificial neural networks are extremely promising candidate models. There are few reasons behind that. Firstly, its ability of neural network to learn nonlinear relations between variables. Secondly, its robustness to noise, which is extremely important if we deal with stochastic cases. Besides that, neural networks can be easily implemented in parallel. However, there are also a few disadvantages. The development requires the participation of a human expert, a data scientist or artificial intelligence engineer, and time of such experts is valuable and expensive. Besides, neural networks can be hard to fine-tune. Fortunately, there is an approach capable to kill two birds with one stone, namely machine learning automation, or simply AutoML. From engineering point of view, it's quite convenient to think about artificial neural networks as if they are a collection of architecture specifications and hyperparameters. A sort of building blocks. This includes depth, how many hidden layers does the network contain, width, how many neurons are within each layer, and various hyperparameters like activation functions, optimizers, learning rates, momentum terms, and many, many other. So the core idea here is that we can play around with these building blocks in the attempt to produce good models, as if these blocks are sort of Lego pieces that we may rearrange in the order that will correspond to what we want. As the result, the whole process can be automated in the following way. Let me show that. So firstly, the vector of input parameters is generated. A simulation model is run n times in order to produce the output y. Both vector of inputs and the output are concatenated and labeled. And if this procedure is repeated in the loop, a data set can be generated. After that, the data set is split into training and test samples using k-fold cross-validation. After that, genetic algorithm is, well, that's oversimplification, but genetic algorithm is searching for such an architecture that can be trained on the train sample and demonstrate the highest accuracy on the test sample. We considered two problems to test the proposed framework. The first one is the inventory control system that deals with perishable goods, or just PIS. This system takes advantage of QR, or also known as RQ, also known as SQ inventory control policy. The idea is very simple. As soon as inventory level reaches a particular threshold known as reorder point, a new batch of a size Q is placed. And Q is known as order quantity. The model is multi-product. Demand is stochastic. Here you can see that backlogs are not allowed. Goods are perishable. Namely, every batch has an expiration date, and when the expiration date is over, the batch or the lot is lost and has to be shipped back and recycled, which causes extra expenses related to reverse logistics. Net profit is an output of interest and subject of maximization. The model also incorporates discounts and implemented as a discrete event simulation model. In the second problem, we deal with the multi-product production inventory system. Demand is non-stationary and modeled using the Markov chain. Such type of demand is also known as Markov modulated demand or simply Markovian demand. So for every product, we have to decide when to start production and when to stop production with regard to constrained inventory capacity. The model incorporates lost sales and also implemented as a discrete event simulation model. We consider 10-product case of the PIS model and the 4-product case of the MMPS model. Models contain 151 and 81 independent variables for access, respectively. The obtained output is averaged and labeled. And by repeating the procedure described on the previous slide, 2 data sets of 600 observations each are generated. Both data sets are split by training and test subsamples using tenfold cross-validation, such that a classifier is expected to predict the label for such vector of inputs that has not been encountered during the training phase. The evolution lasts 10 generations, and each generation is populated with 40 classifiers. In 10 generations of architecture morphism, the classifiers with the average F1 score of 0.96 have been derived for both PIS and MMPS simulation models, which is just a coincidence that these values are the same. And it's also essential to point out that in both cases, the variance of when F1 score calculated using the tenfold cross-validation is insignificant, which implies that the classifiers were able to learn and generalize well. Here we can see how accuracy, precision, and recall are improving as the classifiers learn. And this table contains the specification of architecture and hyperparameters. Here I wish to emphasize that both models have several important features in common. Firstly, they are quite shallow and contain only 2 hidden layers. Both of them take advantage of Adam-based optimizers, which emphasizes the importance of momentum in the learning process. And the success of SILU, or scaled exponential linear unit, can be explained by its property of self-normalization, which helps against the vanishing gradient. Finally, conclusions. First, we may conclude with the statement that the classifiers derived using the proposed procedure can learn and generalize complex nonlinear relations within the simulations. It's important to point out that both components within the proposed AutoML framework are strongly associated with these so-called no free lunch theorem. And according to the theorem, there cannot exist an algorithm for solving all possible problems that is in an average case superior to any competitive one. Yeah, and this statement is true for both optimization driven by genetic algorithm and supervised learning performed by multi-layered perceptron-based classifiers. In this regard, in the general case, the question of whether the proposed approach is inferior or superior to any alternative has no sense at all. However, the following can be highlighted as undisputable advantages of the proposed framework. Firstly, automatism. Such labor-intense and time-consuming steps as sampling, labeling, neural architecture search, hyperparameter optimization, and performance evaluation are fully automated within the proposed solution, and as the result, do not require the participation of human experts. Second, parallelism. The essential components of the proposed framework, genetic algorithm and multi-layered perceptron-based classifiers, are implemented in parallel, so that computations necessary for genetic operators and learning can be distributed across different processors, including tensor processing unit, for example. And universality. Both genetic algorithm and multi-layer perceptron are universal and task unspecific. Namely, the universal approximation theorem justifies the universality of multi-layer perceptron, and Holland's schemata theorem or schema theorem highlights the universality behind genetic algorithm. With this, I end my talk. Thank you for attention.